not doing it, then that means I forgot for sure. Never hurts to just say, hey, Mike, don't forget to record, and I'd be really appreciative. Oh, we're just about there. I have a psychological need to start right on the minute, so we'll always just watch those seconds and begin right as it starts. But the good news is if you jump in right at 6 o'clock, you didn't miss a single thing. And hey, it's time to start. Welcome back, everyone. Well, we have several new faces in this class. There seems to be lots of kind of change in the registration of this class from Monday to Wednesday. So just for a quick rundown, all of our classes are going to be recorded. So if you go here to the record lectures link near the very top of the Canvas page, you can see everything that we discussed on day one, discussing the syllabus, things about testing were the major discussions we had. We did a little bit in section 5.1, and any work we do gets re-uploaded here, so you always know exactly where we left off. We're still on example one. We didn't make too much headway. I also will be posting the next section ahead, just in case if we got through section 5.1 today and we have some extra time. If it makes sense, we'll take a look into the next section. But I publish it on the next week since that's likely the time we're going to complete that one. Except we're already due for a holiday, as this announcement says. So after today's class, we'll reconvene in a week away from today to work in section 5.2. Usually I try to give a quick roundup of announcements and that kind of stuff, and then just turn it over to the class. Any questions whatsoever, folks? Okay, let's get started then. So let's clear this off. We're in section 5.1. The goal of section 5.1 is to define the domain of our trigonometric functions. And in section 5.2, we define two of six, the sine and cosine function. So before we even say what are the trig functions, we still have this work to do, just determining what are angles. And our initial example was just to say once and for all, mathematically, what do we mean by an angle? We form two rays, one called the initial side, the other a terminal side, and the measurement between the two on a common vertex is the angle that we're referring to. There's a lot of angles that we can draw just to start out, but really the big challenge of section 5.1 is a lot of people have an intuitive notation of what an angle is, but we want to define them in radian measure. Yeah, go ahead, Andrew.
If it isn't stated, is there any way to know the difference between the initial and terminal side?
It would have to be stated,
Okay.
except there is one convention. This convention is if the angle is stated to be in standard position, then it's always a given where your initial side is always going to be. Let me match my color coding here. Oh, I didn't actually color code that. For angles measured in standard position, the initial side will always be the positive x-axis. So
Okay.
that's our one thing that's going to be a giveaway for us on that. Other questions so far? Okay, maybe another answer I could give. It's not the best answer because this angle could have been drawn in this way, which is just completely fine. It's saying it's formed between this ray and this ray. But if ever we want to be really specific, another shorthand way of saying it is put an arrowhead on this right here as you form the angle. And then it is a de facto way of saying this side should be the initial side and this side should be the terminal side. So there's a kind of a second way to see. But the trouble with that is the arrowhead is not required when people draw these angles. So it's up to whoever's drawing them to decide, do I want them to have that context of what's initial, what's terminal? But other questions at the moment? Okay, example one is meant to be a pretty light example. This would never make it as an exam question. Really, it's going along with the definition. And like I mentioned before, we all have an intuitive idea of what angles are. For example, if someone says 90 degrees or 360 degrees would mean one full rotation. 100 degrees would be to just turn completely around, face the opposite direction. So let's just put some down just for the sake of writing out some familiar angles. We mentioned before, there's now a big role the positive x-axis is going to make. So oftentimes when I go to draw an angle, I will put down an x and y plane. So I won't always just write down just random rays in some weird point on space. So now my vertex is going to be the origin of the x-axis. So here's our new vertex. This will just be assumed when we start drawing angles. I'm going to let the x-axis be the initial side, kind of going on along with the definition we peeked at. So going this way, this is the initial side. And let's draw some angles, maybe one in green for the terminal side. If I have an angle that goes maybe about like this, we could call this angle theta. It's still going in the same counterclockwise direction, which is curious. There's going to be a reason for that later on in the notes. And if you had to say what this degree measurement is, well, that's kind of tricky. We don't have any tools to really measure. And a lot of what we're doing in class, you just have to use a bit of your imagination. I'm not perfect at drawing angles, and I'm definitely not an artist. This one is meant to be 60 degrees. So that would be a 60-degree angle. And that's because if we rotate it all the way, oh, that's not working the way I intended. Let's Control Z that. If I rotated it all the way up to here, it would have been a 90-degree measurement going from the x-axis to the y-axis. So that's just 30 degrees away from the y-axis for a 60-degree angle. Okay, let's draw another one just for the sake of fun now that we're looking at this. Another angle we could draw is if I go this far, that's 90 degrees. Go this far again, we're now at 180 degrees. Go this far again, we're at 270 degrees. So if I just go 30 degrees further, the angle would look about like that. And we would call this one a 300-degree rotation. It's kind of hard to put it on the diagram now. The diagram became really busy. So here's another convention we sometimes take. We don't always put the angle theta right here in between the rays. Our initial side is this ray, the positive x-axis. Our terminal side is right over here, where this ray terminates. Sometimes we just put the angle right here on the terminal side itself in this kind of way. That's all right out. Let's not use theta again because it already has a meaning. That'd be a conflict of notation. Let's go to the other angle, phi. Some people might say phi. I'm not Greek, so I'm just going to go with phi. That's what my math professors said. So this one will be 300 degrees. If we went to a full rotation, that would have been 360 degrees. And we can rotate as many times as we want for maybe next 720 degrees and so on. But those are just some common angles that a lot of us are used to writing down, used to visualizing and thinking about. And this is just a mathematical definition of how do you define angles in the very, very first place. Any questions at the moment, folks, with this example here? Okay, we need to put in a little bit more structure here. And one thing that we mentioned again is all the angles I've drawn are measured in the counterclockwise direction, which is an interesting convention. And one way to think about this convention is if we were in this side of the plane, we'd be in quadrant 1. This side we'd be in quadrant 2. This side we'd be in quadrant 3. And over here we're in quadrant 4. So there's already a kind of interesting positive rotation about the plane, where if you go counterclockwise, we think of that as positive. It's an interesting convention. So now going to the next definition, here's where we're going to start drawing negative angles. If there's a positive angle, there should be negative angles. And a 0-degree measurement means the initial side is just the terminal side. And this is how we determine them. If we rotate counterclockwise, this will result in a positive angle. So counter is for positive. And if we rotate in the clockwise direction, that will result in a negative angle. That's kind of an interesting convention. Some people have asked in class very often when this comes up, why? Why is counterclockwise positive? That's not how clocks work at all. So it's already kind of weird, right? But there's lots of different kinds of reasons this is a good convention. My explanation of that's how the quadrants are drawn out from quadrant 1 to 4, that's an okay way to explain it. But another bigger explanation is it comes from physics. If you end up being enthusiastic about physics, maybe you know a good deal about it or you're about to. This comes from a convention known as the right hand rule. It's an interesting convention in physics that just comes up a lot. And the idea is if this is a plane that we're dealing with, let me make sure that this is actually showing up on camera. If this is a plane that we're dealing with, then you put your right hand on the plane. Notice that your thumb is pointing up, perpendicular to the plane. Well, sort of, just imagine it is. Then the direction your fingers curl is considered the positive direction. But that's naturally the counterclockwise direction. And so that's where this convention comes from. From things in physics, they came up with a right-hand rule that makes a lot of stuff easy to work with and consistent. And we just carry that down into trigonometry as well. So we'll just draw a couple more angles, still getting used to the writing down angles. Now with the understanding we're dealing with both positive and negative angles now. Any questions at the moment? Okay, I'll just draw some random angles. Again, example 1, example 2, not really real homework problems or exam questions, just getting started with the definitions. So here's our new XY plane. This time the XY plane is a little bit more important. You don't have to write or label the X and Y axis. If you draw this down on paper, it's going to be automatically assumed this is the X axis. But just to tie in the definition about an angle in standard position, this is now going to be another convention. If we write down a plane like this and start just dropping angles on this plane, we're always going to assume the positive x-axis is the initial side. Initial side. Since we're always going to assume our angles are from here on forward, measured in standard position. If they're not, we'll have to say something to explain why. So as long as we make it clear from the context, we don't necessarily have to say this is the initial side every single time. That will just be our assumption. So let's draw some angles, positive, negative, using degree measure. Don't know why I went that color. Let's stick with it. If we go with a negative degree, let's go maybe this right here. If I rotate from the red dot to here, that would be negative 90 degrees. So if we go just halfway and rotate this far, so here's our rotation going this way, this would be negative 45 degrees. This time I didn't give it a variable name. I didn't call it theta equals negative 45 degrees. But I did put the arrow here just to indicate if we rotate this way, that's the reason why it's negative 45 degrees. You could have left it just like this and declare this is negative 45 degrees, and that would be totally correct as well. Let's put in the arrow just to be explicit. The reason it's negative is because of the clockwise direction. So from up here. One thing that's kind of limiting about Microsoft Word, by the way, is they only give me 3 pens, so we have to be kind of fast about swapping them. But at least it gives us a little bit of mental break between writing things down. Our goal is not to write stuff as fast as possible necessarily. So now next, if we go in the counterclockwise direction, we'll get a positive angle. And so let's go maybe, how about this far? And this is, again, not easy to guess, especially when we're getting used to this. But if you had to guess the degree measurement of this angle, anyone see what it would be?
I'd say it's probably about 100 or 110.
Yeah, absolutely. I was going for 120 degrees, so your assessment would be spot on for something like that. Good eye. So my thought was, again, it's not drawn perfectly. It's all freehand, so it's really hard to tell exactly. If I rotated this far, though, that would have been 90 degrees, right? And if I add 45 degrees to that, I'd be out here. Notice these lines would look like they are a straight line now. That would be 90 degrees plus 45. This is clear out at 135 degrees now. So saying that this looks like about 110, absolutely. I'd say that'd be spot on, right in the ballpark of eyeballing it and me freehanding it. That'd be an acceptable, great answer. Here I was going for really 120 degrees. I notice this time it has a positive sign because we rotated now in the counterclockwise direction. So now this is always kind of weird. If you go in the clock direction, clockwise, you are dealing with a negative angle, and counterclockwise will be the positive direction. Any questions so far to this point? Oh, sorry, I just missed your statement right there, Luke. Not quite 135 degrees, but honestly, doing this freehand, it is very close as a guess as well. Okay, yeah, looking at this, that's supposed to be 30 degrees. You know, it might have looked a little bit better if I was closer to about there. So if you felt it was closer to 135 degrees, yeah, the more I squint at it, that seems about right. So 120 degrees. One thing I want to reiterate though is you don't need any specific kind of graphing paper. You're not required to have any kind of tools like a compass and protractor or any kinds of things like that. I will have some diagrams that show these angles in a more exact position, but it's very educative and helpful to try to draw them yourselves. And that's what we're attempting to do right here. I think with my revision, this looks a little bit better as 30 degrees off for an actual 120. So that's the domain of our trigonometric functions, just angles, whether they are positive, negative, or zero. The 0 degree angle is this one, where the initial side matches the terminal side exactly. But here's one big problem with trigonometry. Its use is in calculus, engineering, physics, and in all of those disciplines, we don't use degree measurement very often. Instead, we use something called radian measure. So that's where the notes gets a little bit tricky. Sometimes that's the new concept for everyone in the class. Radian measure is going to be used almost always throughout this course, which is helpful in your further courses that are going to use this. But we'll see sometimes where degree measurement does make more sense, in particular for certain applications. So it's not like we're throwing away degree measurement. What we need to do next is define radian measure and show how to convert between the two systems of measurements for angles. So that takes us to our next definition down below, the definition of radian measure. So this is pre-calculus 2. The topic is trigonometry, but the full name of this topic is really unit circle trigonometry. So it's no wonder that circles are going to make into this picture here. We're going to say our angle is now going to be placed at the vertex of a circle at center of a circle rather of radius r. So now there's a circle on the menu here. Highlight that. And we define radian measure through this text. S is the arc length, and radian measure theta is S divided by R, where R is the radius. And the new unit is radians. That's kind of a tough definition to track without a diagram, so I think I forgot to actually put this white space right here. Sorry if you printed this out or if you're working on the PDF. I put this in after the fact once I noticed. But usually when we have a definition like this, our job is to illustrate it to just better understand it. So we want a circle of radius r. I'm going to place my circle and its center right at the origin, like we've been doing before. So there's an XY axis. I usually will leave off the X and Y description here. So here's our circle. I'm not great at circles, so this one looks more like a rock, but we'll get better at it as time goes by. If you're not very artistic either, you're not using any special tools, that's okay. You're never going to lose points if your circle doesn't look perfect. But one thing I found that helps is try to draw them fast and they come out better. The more I try to think about it, the more they're going to start to look like a football or something like that. So there's my circle. Since I placed the center of the circle right at the origin, and because the radius is r, going this way, that means there'd be coordinates here. This would be coordinate r0. The radius was 5. This would be at coordinate 5, 0. There's a coordinate here. This would be at coordinate 0, r. And now we want to allow this line to be the initial side, since we're measuring in standard position, and just draw some angle. In this diagram, I'm going to have my angle terminate, say, out here. You can have it terminate in any quadrant that you prefer. I feel like it just looks a little bit better on this diagram. So from going here to here, mine is measured positive, but it could be measured positive or negative. This is my angle theta. So the thing that's new on this is S. S is the so-called arc length intercepted by the angle. That's a heck of a statement, but what they mean, I don't think I can click on the angle just yet, is what they mean here is when we start on this initial side, angles you can think of as a movie progressing and the rotation happening continuously until it just stops here. So as the angle rotated, the arc length is the part of the unit circle going around like this that was intercepted by this angle and terminates right at this spot. So the length of that is S, arc length. Already there are a lot of moving parts here. We have the radius of the circle, the angle measurement inside, and the arc length so far. If you put all of that together, let's just rewrite the definition, use our own handwriting, kind of helps internalize it. The more things you do with your mind, your hands and such, the easier this stuff is to just kind of seep into your brain. So theta is the angle that we're measuring now from here to here, and it's going to be S divided by the radius r. What's kind of amazing about this is the radius r has no bearing on what their angle measurement would be. We could change the circle to be twice as big, half as big in radius, and it'll still measure the correct angle theta. So that's our brand new definition. This has units, radians, but we can shorten that to rad as a common shorthand as well. And another thing that's interesting here is that's an optional unit. If you write down something like theta equals any number whatsoever, the automatic de facto default unit everyone will assume is radians. So this is an optional unit since radians are the default. Again, that's kind of weird if you're new to radians. Something that seems kind of unnatural at first is now our default way of measuring an angle. But any questions at the moment with the definition before we try it out? Okay, let's give this a try then. At this point, we're starting to do problems that are pretty similar to what you're going to see in the actual homework assignment. We're going to do some work on just defining what the radian measurement will be in this particular circle. This is a tough problem when you see a problem like this in the homework because there's no diagram, but trigonometry happens to be a pretty geometric kind of subject. The encouragement for these sort of problems is just draw your own. It could be just on your scratch paper, but it's a good idea to just have it there on your assignment. So then when you look over your assignment again, you see how it all comes together. So we're told we have a circle of a radius 10 meters. The XY axis is pretty optional here, but just for the sake of having it, it'll be useful later. I'll also include it on this one. So here's our circle. The radius is 10 meters. That's this distance going this way. We have a positive angle theta that intercepts a length of 43 meters. That's kind of hard to visualize, so we'll just do the best we can. But imagine this green segment here, really just the line, imagine the line shaded green, is able to bend. Maybe it's a string now, and you're just fitting it across the radius, or excuse me, the circumference of the circle. To me, that would look like about, maybe a little too far, but just about 10 meters. We're going for 43. So do it again. That's about 20. It's not going to be perfect, so we're just freestyling this. This is maybe about 30. And so 43 to me looks like it would land right about there. So here's our angle. Terminates out here in that ray. So here's theta. And we're told something about this arc length S. S in this diagram is 43 meters. So that's just the length of the position from right here on that solid dot to that second solid dot, going from here around to here. I feel like that's helpful to highlight as well. What's not known yet about this diagram is, what is theta? I drew it in a counterclockwise since we're told it's positive. And our goal is to find the value of theta in this diagram. Any questions so far? Just building it up. Okay, let's write it out. A lot of the work here is really just tracking the right definition. So if this was a homework problem or an exam problem, what you would want to do is say, well, what is the definition of radian measure? It's going to be theta equals S divided by R. Then we just make a lot of substitutions, as many as possible, just 2 in this problem. A lot of the mathematics that we do ends up being just a series of substitutions, and trigonometry is no different. Find the information on S. Notice you might not have needed the diagram to really solve this problem, but it's helpful because the idea is understand the angle theta. So having this whole picture is really kind of the main point of the problem, even though solving the problem is just a really fast computation on the right. So again, if this was a homework problem and you just gave me this over here, I'd say that's completely fine. I'd assume you might have had this as your mental image, or maybe you did it on scratch paper just to see how it all goes. So S is going to be 43 meters, carrying the unit in. Radius is 10 meters. That unit carries in as well. But then we have a cancellation of units, and that's natural for radian measurement. The units will always cancel out, and we're left with 4.3. We can say 4.3 rad if we want to be specific. Let's do that one more time. But very often in this class, I'll leave off the radian measurement unit and just say 4.3 is the radian measurement of theta. So all it's telling us is, how many radii did you have to stretch out till you got to your terminal position? That's why it's called radian measure in the first place. It's all based off the radius. Well, any questions at all, folks, with that first, I guess, example 3 on this one? Okay, so radian measurement is a tricky idea because really that's an equation with 3 variables. But if you could see it as a picture, this is where it really all kind of comes together. All we're attempting to say is, how far did the terminal side rotate in terms of radiuses? So we make the arc length measurement, divide by the radius, and that is now our new way to measure an angle. But the moment you take an old way, like degrees, and define something new, like radians, we now have to do the work of, how do you convert from one measurement to the next? That is also very useful and very important. So that's what we're going to look into very next. And there it is. This formula tells us everything. Pi divided by 180 degrees is 1. So therefore, the reciprocal, 180 degrees divided by pi, is also 1. And there's nothing further to say about that. That's essentially our conversion factors. But that's kind of dissatisfying to just park right there. I mean, we can use this formula, immediately start solving problems like these ones over here, converting it from radian to degrees. But occasionally when we have a formula like this, we spend a little bit of time with it because understanding what it's really saying and how it comes together is just as important to the formula. So we'll do a few of these so-called derivations. We're not going to do a lot in this class. We will do a good derivation when it makes sense. It helps us reinforce the prior concept, what radian measurement was in the first place. And if it doesn't take too long, some derivations are just complicated. When that happens, I'll often just show a diagram so you can see how it comes together. And if we get a little bit behind class, sometimes we might skip a derivation just so that we're not getting too bogged down when we have other as equally important work to get into. But I think it's educative to see how these conversion factors come into play. So let's start. In our derivation, I don't know why I pluralize it. Let's just call it a derivation. The new object we need is the so-called unit circle. Our unit circle is a circle with radius, one unit, whatever the unit might happen to be. And the next feature is the center is at coordinates 0, 0 in the xy plane. So it's kind of the nicest circle ever in a certain sense. Center is right at the origin, and we want radius to be exactly 1. Let's sketch that out. That's a horrible circle. Let me try one more time. That'll work. It kind of fell apart over here. But again, your imagination is important for a lot of these freehand drawings. Whenever we say we have a unit circle, it means there's also an algebraic equation in the background. The equation for this circle, centered at 0 with radius exactly 1, is x squared plus y squared equals 1. So that's the equation for this circle that we see right here. Because it's x squared plus y squared equals 1 and the radius is 1, it also tells us that right here we have coordinates 1, 0. Up here we have coordinates 0, 1. And that's just because that's the length of the radius going from here to here, here to here, and so on. So now that we have a unit circle, let's do a measurement on this. We've drawn a few angles, so let's just draw a whole new one. Let's go from, how about here to here? Just a half rotation this time. Anyone see what the degree measurement should be if we rotate halfway? Oh, I missed a chat. Absolutely, thank you. That's going to be 180 degrees all together. So rotating halfway in the counterclockwise direction gives us the 180 degrees. And, well, that's helpful, right? That shows up here and here in both of our conversion factors. We need another idea. We rotated from this position to this position. Then we also have an arc length that we can deal with. It goes from here all the way out to here, and that is S, arc length. We need to also bring arc length into the picture because if we're trying to convert between the two, the numerator is in radians with a rad unit dropped, the denominator in degrees. Radians requires an arc length to be in the picture. Now here's the next idea that starts to tie all this together. We also have a formula for the circumference of any circle. The circumference equals pi, 2 pi. Let me control Z that out of there. 2 pi r. not pi r. I'm not sure where that was coming from. Our circumference is 2 pi r. In this problem, though, recall radius is just 1. So that means circumference is just 2 pi times 1 for a 2 pi. But then think along the lines of, well, what is a circumference? That's just the whole perimeter or the entire arc length if we rotated 360 degrees. If we rotated just halfway, we know the arc length. The arc length is just half the circumference. So let's say here, since theta rotated halfway, S, which is arc length, is going to be equal to the circumference divided by 2. Because once again, circumference is rotating all the way. But if we go halfway, we just divide that result by 2. We make a substitution in the numerator. Coming from over here, the numerator we found to be 2 pi. We're dividing that by 2, so S is just pi. So now we have two things on the table. On one hand, theta is 180 degrees in degree measurement. But on the other hand, we can say this. Therefore, theta, and this is tough already because you just looked at that definition for radian measurement, and now we have to use it immediately. The definition above, if you're to scroll up in your notes, is take S, the arc length, divided by R, the radius. So that's our definition from the last page in the notes. Now, like we mentioned before, loads of substitutions, but this is an algebra class, so it's kind of par for the course. Substitute in place of R, the arc length that we came up with, which is pi. Here's the nice part. This is one of the reasons we like the unit circle, radius 1. We're substituting down below here a radius of 1 as well. So that then means theta equals just pi, and I'll say rad for the measurement specifically here, just as a reminder, we use the definition of radian measurement. So now two things has happened. On one hand, theta is equal to 180 degrees. On the other hand, theta is also equal to pi radians. If you have one variable equal to two things, well, those two things have to now be equal. So we can wrap this up, or put this all together rather, by saying these little fancy triangles is just another way to say therefore, or here's my big conclusion. 180 degrees is equal to pi radians. And so this is just an ordinary equation from which you can either divide 180 degrees on both sides, you get that result, or you can divide by pi radians on both sides, and you get that result. I'll divide it once so we're not saying too much stuff all at once. We can just say 180 degrees over pi equals 1. And that's the second conversion factor right here. So that's our derivation. All it does is tie together the definition over here for radian measurement, uses an extraneous idea of the circumference of a circle, and the fact that we used the unit circle wasn't critical. This would have worked for any circle whatsoever. It just made some of our work a little bit easier since R dropped out. Well, any questions, folks, with the derivation so far? Okay, so now we have two conversion factors. We should say what their good uses are. This conversion factor is one that you'll use to convert from degrees to radians. And you can tell because if degrees is in the denominator, that's the unit that would be canceling out. This one's trickier to see because we don't always write radians in as the unit, but sometimes pi is a giveaway that you're probably dealing with radians if you see that down below. in this context. So with pi in the denominator, radians would be canceling. You're going to get a result in degrees. So this one is going to be to convert from radians to degrees. So those are the use cases for both of the conversion factors. What we'll do next is just practice working with this. We're nearly done with the notes, but I'm noticing we're also nearly done with time today. I thought I was going to get a little bit further along these notes yesterday, but that's okay. What will happen is if we don't finish these notes today, after class, what I'll do is make an adjustment here. I'll move the assignment over and the notes over to the next week down below, and then we'll just have this due date moved. So that's always a week away from when we fully finish the notes. But any questions at the moment? Okay, let's do just a few arithmetic type problems to finish out these ideas. And then we'll call it a day and go on holiday, reconvene back on Wednesday of next week. So these problems right here are pretty now quite similar to the ones that you're going to see in your homework set on section 5.1. It says here, for example, 4, convert each radian measure to degrees. And we're also doing one additional thing that you must also do on your homework. Plot the angles on the unit circle. You can plot it with the degree measurement or the radian measurement. It's completely up to you. But part of the purpose of this exercise is later on, when we're further on in chapter 5, when you see negative pi over 6, you need to know where the terminal position is of that angle so that you can calculate cosine of that angle or tangent of that angle and so on. So part of this is more visualization for us, so we get better and better at evaluating these trigonometric functions. So you might already know where negative pi over 6 terminates. It's going to be in quadrant 4, but if you're not sure, like probably most people in the class, if you're seeing this for the first time, that's the reason we might want to convert to degrees. We're just trying to get better intuition on this angle. So first we're going to say go negative pi over 6 is going to be equal to negative pi over 6 times, and we want a conversion factor. We're going to use the one that puts the degrees in the numerator and pi radians in the denominator. That gives us just an immediate cancellation from here to here. Pi is gone. The radian measurement angle that we never indicate as a unit is gone as well. And 6 goes into 180 30 times. So this turns into negative 30 degrees. At that stage, half our work is done. We've converted it from radian measurement into degrees. And plotting on the unit circle, some people might just do it this way. You might just draw a circle, and that's okay with me. For me, though, it looks a little bit better if you use the x and y axis. I know it's going to be more helpful down the line when we define the trig functions to have these axes in place. So I'll usually show it this way in the notes with an actual axis. And negative 30 degrees would be right here. Let's say that's also negative pi over 6, just to tie the two ideas together. So that's one down, one conversion off the table. Any questions at all, folks? Getting used to that angle there, negative pi over 6. Okay, big takeaway on this problem is if you have pi in your numerator and something over 6, this means you're changing by, let me make that a full statement, moving by 30 degrees. We just happen to move in the clockwise direction. That's why the negative sign there. This one's positive, and along similar lines, let's spill the beans on this one. If you see some multiple of pi divided by 4, that means you're moving by 45 degrees instead. Luke says, would positive pi over 6 be the same as positive 30 degrees then? Yeah, absolutely. Positive pi over 6 would have taken this angle and would have had it terminate out here, now in quadrant 1 instead of quadrant 4. Other questions at the moment? Okay, well, let's try this out again. Really, there's not a lot of real algebra arithmetic happening here. We're just picking the right conversion factor and simplifying down. So let's try it again on pi over 4. That's an awful looking pi. Let me try again. Take pi over 4 and write that this is equal to pi over 4 times same conversion factor, since we're converting in the same direction, radians into degrees. Then same idea, simplify as we go. Now, 2 goes into 4 twice, into 180 90 times. So that means 4 goes into 180 45 times. And this comes out as then positive 45 degrees. So our quick sketch of this one is going to look like this now. So we started with pi over 4. That's a weird measurement. But it turns out, now that we've converted to degrees, we have a little bit better intuition. This is 45 degrees, which is equal to pi over 4. So that's just 1/8 of a full rotation. We ended up right over here. We would have been at 90 degrees instead. That would have been pi over 2 instead. You'll see similar problems in the exercises. So that's a 1/4 rotation. Only going halfway then is a 1/8 rotation, ending here. So the next natural thing is to go in the other direction. Let's maybe do one more problem, call for questions, and then we'll call it a night. Any comments at the moment? Okay.
Remind me again why that meant moving by 45 degrees.
Oh, that means moving by 45 degrees says when we took this angle right here, it started really right here on the initial side. And because it was positive, we moved 45 degrees in that direction to end right there. So that divide by 4 is telling us we're going in about a 45-degree increment. Whereas on this one, when it was divided by 6, some multiple of pi in the numerator, we moved by 30 degrees, but in the clockwise direction, so the negative sign. Does that make sense with that? It's kind of cryptic. I can see what you mean. Does that make sense by moving by 45?
I'm not sure
Okay.
I get it, but I'll try and I'm sure I'll catch on.
Sounds good. That I understand the feeling on that. Another thing to think about is if it was, say, pi over 4, it ended up right here. So we rotated by 45 degrees. But what if you doubled it? That would have been 2 pi over 4. And 2 pi over 4 simplifies to pi over 2. It would have been right up here. And then what if you tripled it? 3 pi over 4 means, well, you moved 45 degrees once, 45 degrees twice to end up at pi over 2, 45 degrees a third time. And so now you're here, way out at, excuse me, 3 pi over 4 for this one. So that's kind of a different way to kind of see the same sort of idea. Whatever pi number there is, whether it's 2 pi or 3 pi, tells us how many times did you crank 45 degrees in your rotation. Let me take these off so that the diagram doesn't get too busy though.
All right, that makes more sense.
Also, I'm glad to hear that. Sometimes it's really kind of hard to convey these sort of ideas just because the whole thing is just sort of a totally new subject. But let's try this out again on example 5. Example 5 is kind of the friendly one because you probably already know where 270 degrees is. So let's this time just start with the plot on the unit circle. And 270 is nice. It's a multiple of 90 degrees. It's positive, so we start here and move in the counterclockwise direction. So this would be 90 degrees. Add 90 more, we're at 180 degrees. Add 90 more, 180 plus 90 is 270 degrees. And we've nailed the angle. 270 is right exactly here. And let me convey it a little bit more nicely by showing that angle on this one. Let me put on these two as well, just so we can be specific the direction we rotate in. I would say these arrows are optional, but they just more help out the notes. If you left it off on your homework, that would have been okay. So that one was a clockwise rotation of 270 degrees. But what this question is all about really is, what is that actually in radian measurement? So it looks like it's the last computation of the day. We take 270. We're not going to multiply by 180 degrees divided by pi. We take the reciprocal of that using the other conversion factor, pi over 180 degrees. So if one conversion factor doesn't work, just flip the whole thing around and you're in business. I wanted to start off by saying 270 equals just to make the notes more clear. Then it's the same thing as before. We just simplify. We already know 90 goes into 273 times. So that's going to be 3 pi in the numerator. 90 goes into 180 twice. So that's just 3 pi over 2. So it tells us this terminal position is 270 degrees. But later on in chapter 5, we're going to literally say 3 pi over 2 when we land over here. Much like when we erased, this one was pi over 2. This is 2 pi over 2, which simplifies to pi. But then down here, like we have in our sketch, that one terminates at 3 pi over 2. A lot of the homework is just practicing these kind of ideas so we can see it more intuitively as we get into the next section. And it looks like we're running over by about a minute. Sorry about that. We'll come back here right literally on part B and fill out the rest of the notes when we come back after the holiday next Wednesday. But any questions at the moment, folks?
Well, I guess you just answered, but I was gonna ask if we can do the assignment now, or if you were wanting us to wait on that.
You absolutely could. There's going to be two problems where it's going to look a little bit weird because we haven't gotten into the ArcLink formula application nor the sector area formula application. But really, they're not too bad. You're just using different kind of formulas. If you feel comfortable, I'd say go ahead. You can even turn it in early if you prefer. But there's no harm in just going right up to these problems and then solving them after we do them after class. And if you're the kind of person that would rather wait till all the notes are solved, that would be okay too. Sometimes that makes a lot of sense as well. So really kind of up to your preference. Any other questions so far? Okay. One thing that's a bit of a challenge for me is 50 minutes goes by really fast. So sorry if I didn't get all your questions in. Sorry for running out about a couple minutes later. But I do have some time after class. So if you do still have questions, I'll be happy to help out. Otherwise, have a great night, folks. I'll see you all next Wednesday. And yeah, absolutely, Luke. I just saw that in the chat. Pi over 6 is the same as positive 30 degrees as well. Thanks, folks. Have a good one. Thanks, you too.